Today we're going to talk about Pravega, an open source new storage platform, primarily built for the reactive world. What I mean by that is, this is the golden age for the reactive programming paradigm in general. Why? There are three kind of different things coming in place at the same time. One is the emergence of new streaming processors, which do exactly once processing, which can do batch and real time at the same time. Second is the emergence of serverless computing, even though that's a bad name, but still go with that. That is also becoming very, very popular. Because of these trends, I think we are in a golden age for reactive programming. But as we know, the reactive programming really needs some kind of a messaging underneath the covers or something that delivers events. However, the messaging infrastructure itself has not improved. The only improvement we have seen from 70s when first MQ series kind of software came up is just that the servers are not storing the consumer state. That's the only improvement that has happened, which helped us to scale a little bit better. But other than that, right from the times I have been in college, which has been a long time back, trust me, 30 years actually, we've been talking about same MQ paradigm, similar things, and nothing much has changed. So Pravega is an effort actually to change this and innovate at that level, because all the reactive programming really needs a solid fundamental storage infrastructure for making this happen. So that's why we built Pravega. And we have turned the problem inside out. So we did not start with an events. Under the covers, it's only a byte-oriented streaming storage. And events are put on top of it and not the other way around. So that kind of changes the paradigm a little bit. And we're going to talk more specifically, even though I talked about different ways and different areas it can be useful. Today we are going to focus on the microservices part. So 2 sections to our presentation. The first section, I'm going to talk about what is Pravega, what are the features, and how it works. And then my colleague Mark, we're going to talk about how it applies to the microservices world in general. Okay, so Pravega is about all these things. Unbounded stream data. Most of the messaging buffers are built with the assumption that the data exists only for a short amount of time. Pravega is unbounded stream. That's why it is possible to do batch processing on the same data. You don't need a separate system for doing it, separate storage system for doing it. Permanent and efficient storage. What I mean by that is the ingestion time is very short. We have a 2-tiered approach to storage to make writes very, very efficient. It's very useful for IoT kind of applications in particular, but in general for everyone. The next most important thing is elasticity of streams. We don't have hard static partitioning incorporated, but they're elastic, the streams. That's why whether you're building applications for a very large thing like an Amazon ordering system, or for small streams like IoT sensor sending, it'll work for both of them. I'll tell you why. And then we have implemented one of the most important things. The writes and reads are not impacting each other. Most of the time in messaging systems, when the reads are happening at different parts of the stream and the write is happening to the same stream, there is the performance issues that we'll see. I'll show you why we overcome that. And then the most important thing is we support exactly once and transactions, which is what most of the messaging systems don't do. And then we do it in a very efficient way. I'm going to talk about how we do it. And finally, because we want to make it also a microservices platform, we provide some distributed computing primitives, which makes it possible to run microservice applications on top of it. So these are the things which are different from the regular messaging systems that you have seen so far in the industry. Okay, let's talk about a little bit fundamentals. At the core, as a storage system, primarily treats stream as a fundamental storage primitive. When I say stream, it's an append-only log, basically. It treats stream as a fundamental storage primitive, just as we have files and objects treated as fundamental storage primitive before in the industry. And then we talk in terms of segments. I'll tell you what a segment is. A stream is nothing but a composition of segments, and the fundamental unit of scale is a segment. And all writes are durable. There is no, we only act back after it is replicated in 3 places. So all writes are durable. In fact, you don't even option of non-durable writes in Pravega, because we think it's fundamental. And of course, with stream processing, other things, you can drop the events that are not relevant anymore. But Pravega itself never drops any events, right? It's, as I said, a stream is nothing but is composed of many segments. And a routing key, on every write you specify a routing key which determines which segment it goes to. As write order is preserved per routing key, always. And it is always consistent. And it is built in such a way that both tail reads as well as catch-up reads are efficient. I'll talk how we do it. The most important thing that we should consider is the routing key is you can have as many routing keys as you want. There is no limit on the number of routing keys. There is no strict hard static partitioning here. The segment number of segments grows and reduces as we go along with the stream, right? There are, as I said, there are no architectural limits on the number of segments. Each segment can potentially live in a different server. And it is not, the stream size itself is not limited by a single server. Okay, how we do it? A segment is something that you keep on appending, and at a given point of time, the segment can be sealed, which means after that, you don't write to that segment anymore. After it is sealed, you can write it anymore. But this is an important feature because some of the things that I'm going to talk about, both elasticity and transactions, depend on this particular feature of segments. Okay, let's talk about, but a stream is composed of different segments, but who handles all this in terms of which segment, where it goes, and which all segments belong to a stream, and how many segments you have, is all controlled by what we call a controller. The user doesn't have to control it. But the one fundamental feature of Pravega is this two-tiered storage. What I mean by that is, we can't be both write and read efficient at the same time. What we do is, when we have very small writes, the first tier writes fast. It is optimized for writing only. And then we bulk append it into a long-term storage. Think of it as S3 or NFS or HDFS. These are the 3 protocols which are supported, to which it is tiered down to. But because of this differentiation, what we do is, the tier 1 storage, we rarely don't read from it. It's only meant for durability. When you write, we write to tier 1 storage 3 times and hack it back. And then when you read, if it is a tail read, we read from the cache and give it back to you for streaming applications. But if it's a catch-up read, we read from the long-term storage. But since it's a log, we can read ahead and cache it and give it, right? So that's how we separate the reads and writes. The tier 1 storage is only for durability, but we rarely or ever read from it. Only in failure scenarios, you read from tier 1 storage, okay? So that's how we separated the fundamental concerns. Now let's talk about the different things I talked about. Elasticity. How do you provide elasticity? How can you let stream size grow infinitely? Let's start with one segment first. Don't have to, but in this example, talking a stream with one segment. But we need more parallelism because you have multiple writers writing to the stream. How do we do that? When we see that the volume of data on a single stream is high, we seal that segment and create 2 more segments. Now, the routing keys that we talked about are also split to go along these 2 streams. And this is done automatically based on the load by Pravega. The user doesn't have to do, unlike other systems like Kinesis, where you have to manually do yourself, right? Now, this is how it works. So let's assume on the x-axis we have the routing key space, on y-axis, and on x-axis is time. If you look at it, at time t0, the stream has been split into two segments. It starts with one single segment, then it is split into two segments. By the same token, we also merge when the volume of the data is low. Right? Over time, the number of segments keeps changing automatically based on the volume of the load coming through those keys. So if some keys are hot, it keeps splitting those into smaller and smaller segments. The range of the keys that a segment takes keeps on varying. If you see that, all this key space, I never said it's statically assigned, right? It keeps on changing based on which keys are hot at a given point of time. It keeps splitting when it is high, and it keeps merging when it is low. Think of many of the diurnal applications that you have. In that case, the processors can use or can get signal from the storage system when they can auto-scale up or down based on the number of segments a stream has. It's very important for streaming applications because they have to keep up with the speed at which the data is coming in, and the storage system can tell them when they can auto-scale. I mean, they can or they need not be depending upon the application, but it gives the indication for them to do so, right? So how does it look really? This is the actual graph on our UI when you look at a stream. If you look at it on the top, so the blue color here shows that the volume of data is low, and the red color shows the volume is high. When the stream gets red in the bottom, you see it's a scale-up event, it splits the segment into two. It seals the segment and splits it into two there. Similarly, on the top, the scale down, it's blue, so the volume is low, it kind of merges them into a single segment, right? So over the lifetime of the stream, the number of segments keep varying depending upon the volume of the load that is coming in. So this is how we provide elasticity. These segments can be stored on different machines at any given point of time, right? So as the volume keeps growing, it automatically, so there is no bringing down the cluster, there is no rebalancing, there is no need for changing anything, any configuration, both on the writer side and on the cluster side. It can keep going automatically, right? That's one fundamental difference, how we provide elasticity. And that's how sealing is important, because we can seal the segments, we can move to different machines at any given point of time. And by the way, the controller does all this in terms of assignment of segments to machines in the cluster and all that. You don't have to do anything. Currently, we base it, the splitting and merging is based on the volume of the load coming in. In future, we can have different other things, policies that we can use to do that. Okay. Next is the unbounded stream. Streams are automatically tiered to long-term storage. As I said, we have tier 1 storage and tier 2 storage. The tier 2 storages, things like HDFS, are not good for small writes. They're not designed for small writes, S3, HDFS. Think of any other storage systems, not good for small writes. So that's why we do the first writes in tier 1 storage, which is more a journaling, where we interleave multiple streams and write into a single journal. So it's very, very write efficient, but not read efficient. But we never read from it, as I said. Only in case of failure scenarios, we read from it. But these long-term storage systems are good for throughput. That's why we combine a bunch of writes and put them in the storage after some time. So we asynchronously tier the storage from tier 1 to tier 2, but the user doesn't have to do. The abstraction on the top is only stream. You keep on appending it to one end and keep read from anywhere, right? So that's how it works. So that's why we can give this notion of an unbounded stream, because you're not dependent on a single machine as far as the size of the stream or a partition is concerned, right? You can keep growing it unbounded. Next is exactly once, which is very, very important, because a lot of streaming applications, new stream processors like Flink and structured streaming from Spark have this exactly once feature, because for a given job, they can guarantee exactly once processing. But when we try to batch up different jobs and use Pravega as the sink in between, source and sink for different ones, we can guarantee across multiple jobs exactly once processing, because the storage itself is guaranteed to give you exactly once deliveries, no duplicates and all that. How does it work? So whenever the writer comes up, it is assigned an ID, and it start writing. Here it wrote the first one. So we have that key value with ID and storage on the segment store. Suppose this write happened and never got the AG back. When the writer comes back again, tries to write it, it can have been told that it's already there. So that's how we avoid the duplicate being written. And then it can send the next one because it knows that's already written. This is in the scenario where it's written but never got an AG back, or it has not even been written. In that case, it knows it's not been written, it will write it again, right? It doesn't work only in one scenario when the writer completely crashes, right? Because it doesn't know what its ID is, so it has to come back. In those scenarios, it won't work. Except for that scenario, in all other cases, this will work, guaranteed to work. Because in the segment store, we guarantee this key value is consistent all the time, based on how we write into our tier 1 storage. There is a write fencing implemented there. We take advantage of that so that we ensure on the segment store this is consistent. From the writer side, it always check this and can be ensured that we write only once, okay? Except for the scenario when the writer completely crashes. Now, what if the writer completely crashes? We provide transactions also. How does the transaction work? So whenever you write to a stream, as I said, there are different routing keys, right? Or different segments. Let's think in terms of segments. When writing to different segments, in a single transaction, you can have writes belong to different segments. When a write happens, we lazily create a separate transaction stream. We use streams again for implementing transactions. If you look at the green ones, these are the transaction streams created, and all the appends go to that stream right now. Whenever you write to that transaction, it goes to those streams, the green streams. And when you commit, that's when it gets merged into the main stream. At that point of time, you commit. And we guarantee that it goes in or not. Similarly, you can also abort a transaction. Aborting a transaction is very simple. We just delete the transaction streams, the green streams. That's all, and we are done. You don't have to deal with anything, right? So this is how we implement transactions. This is very important, the way we implement it. We don't do in place in the same stream adding a transaction, because it might lead to issues where you have a long-running transaction, a multiple of them, then some readers might be slow in terms of catching up. That would be the problem with systems which are implemented like that. The other problem we try to avoid is if you have a lot of aborted transactions for some reason, there will be a lot of junk that you need to clean up if you use the same. In our case, we just delete the transaction segment, right? So this is how we implement transactions in Pravega. So between exactly once and transaction, we can completely guarantee exactly once, even in the scenarios where the client fails. Actually, even without transactions, we can implement, that is part of our next improvement that we're going to do. We can provide exactly once even when a client fails. We're going to work on that next. Okay. So that's how we implement transactions. And so let's go over the different features that I talked about. I talked about unbounded stream data, and I told you how we implement that, right? By tiering it down to second-level storage, and we manage the movement of data between those two tiers. The user never sees. Still a stream abstraction. Permanent network, same reason. Real-time and historical data access. Because we are not just depending on file cache on a single machine for one particular partition of a stream, because at different times, the stream could be existing in a different boxes. Because one segment could be one box, second segment could be another box. Because of that, if you're doing catch-up writes and writes at the same time, the reads are not impacting the writes are not impacting the reads, which is a problem when you're writing to a single box, any partition, right? Makes sense? Next is elasticity of stream, and we talked about that, how we are elastic by kind of splitting and merging the different segments and potentially assigning to different box. There is no hard partition problem. We provide transaction exactly once guarantees. We just talked about how we implement that, particularly transactions, which is slightly different from the way most of the other systems have implemented it. And finally, I talked about a distributed computing primitive, which is we provide a compare and swap kind of operation, and guarantee. So whenever you want coordination between two different processes, we provide that primitive automatically. You don't have to use something like Zookeeper on the side just for that. And I'm going to let Mark talk about that specifically because it's very, very important for microservices platform. Right, Mark?
Testing. Okay. Okay. Thank you, Srikanth. No, that's too far. Okay. I think everybody here has been a developer, microservice developer, used to working in a distributed environment. If you're like me, you started before streams became available, you worked in networks. How convenient would it be if all the time in a network, every event you sent out was guaranteed to arrive? Maybe the recipient's there, maybe it's not. The message is still going to get there, and it's going to get there in order, guaranteed. How many of you have implemented the complex recovery logic when the recipient fails, or when the server, the client crashes and has to recover and send things again? That gets really, really complicated really, really quickly. How many times do you find bugs in the happy path of the code versus in all the complex recovery logic? Probably find 90% of them in the complex recovery logic. What if we could get rid of all of that? What if it just automatically worked the way you wanted to? What if item potency you didn't have to think about? It was guaranteed for you. What if you didn't even have to monitor the system? Srikanth talked a lot about the automatic scaling and elasticity of Pravega. Well, what if you apply that to microservices? You can implement your microservice. You don't have to worry. You don't have to be self-monitoring. The system will do that for you. It can automatically adjust underneath you and simply tell you, hey, you may want to increase your number of readers because the system can now support that. What if all the state you had to keep? We've talked a lot here about event-driven architectures, keeping state in memory, all the automatic persistence. I mean, obviously, if you keep state in memory and your system crashes, that state is gone. It can be automatically persisted underneath you, so you can simply recover, again, without that complex logic. A lot of benefits that can become from combining streams in a microservice environment. With Pravega Streams, it makes these benefits even better. Using those capabilities around the full elasticity, that ability to do catch-up reads way back, however far back you want to go. Using transactions, you can have a whole series of microservices with full exactly one semantics. And we'll go through all of that and how that can work. So we're going to start just with a couple examples, kind of generic streams. If you were here, you heard Jonas's talk yesterday about event-driven architectures and so on. It's kind of a very short recap of that. But we'll see how Pravega makes these capabilities even easier to use and even better. You can start with a microservice, and it's writing events to a stream. And here I've shown it as one single microservice, but maybe it's 10 instances or 20 instances, or maybe it's a single instance. It could be anything. But a full event-driven architecture as that data is being written out. It's being picked up by some other service. Here I've said it's a query microservice, but it could be anything. This was originally, I was thinking of the CQRS pattern of the command and query responsibility separation, but that could just be a different processor or something else. And that service is picking up the events and doing whatever business logic is necessary to process those. It can have its state in an in-memory data structure. What's nice about this is in terms of the microservice developer, you can design that in-memory data structure exactly for the job you're going to do. You don't need to worry at this point about how can I persist this to disk, how can I recover, any of that logic. You simply make it a hash table, a linked list, whatever data structure is going to be best suited for the job you want to do. So what happens on failure? What happens when that service crashes? And this is where the power of streams and that ability to go back in time makes a big difference. You simply restart that service. It could be restarted on the exact same node. Maybe it was simply a software bug or something like that. Or maybe the entire node went down. There was a memory fault or something else, and that node isn't rebooting again. So it could start up somewhere else. And how do you recreate that in-memory state? You simply reread from the stream. Theoretically, you could reread from the beginning of the stream. And what would happen in that case? What kind of recovery logic do you need? You're processing the exact same events in the guaranteed exact same order and applying them to that data structure in the exact same way you originally did. In this case, the recovery logic and the original business logic are identical because you're guaranteed to get the events in the same order, process them, put them in that table. Now, obviously, if you've been running your microservice for a long time, it might get a little bit ridiculous and time-consuming to truly go back to the beginning every time. So you can do a checkpoint. A little bit of code which can translate that in-memory data structure into a series of events, an optimized series, which can be used to quickly reinstantiate that data structure and then replay the events in the log from where you failed. But again, it's no complex recovery logic. That service at the bottom, there's this service at the bottom, when it has restarted, doesn't actually know, is it replaying these events due to a failure, or is it simply seeing them for the first time? It sees the event, it applies it, it does the necessary business logic, and it doesn't know. So it really makes that a lot simpler. How about the elastic scaling? What do you do inside a microservice as you're running on the system and you see that the load is starting to grow? First thing you do, generally you add some more instances. Here it's a fairly simple case. In this particular case, let's say the volume of events on the stream is not very large, but for whatever reason you're getting hammered with queries. You could simply have 3 of those services all reading that same event stream, all applying those same changes to their in-memory data structure, but you've tripled your query bandwidth. And maybe tripling isn't enough, maybe it's quintupling or whatever you need to do. But the point is, very small change can respond to that. The other case, of course, is what if it can't keep up with the event stream? Events are pouring in too quickly, and the query microservice can't read and process them quickly enough. And in that case, you can go through and you can use a partitioning scheme, where if you can partition the events, you can have your processors at the bottom. One service takes one set of events, the other service takes a different set of events. Obviously, your queries then need to be partitioned also between those 2 systems, but you've scaled it up in a way that you basically doubled your bandwidth for processing the events. Depending on what you're trying to do, you can scale the reads or writes appropriately. And those could take over. What Pravega does in this case, Pravega makes this all much, much simpler. And the big reason why is because Pravega allows this all to happen dynamically. Pravega detects the condition for you, and Pravega can do it without any business impact. And those are huge differences compared to some other solutions that are out there. So how does Pravega do this? How do we use those capabilities to implement that? We can start with a very simple case. And again, our microservice over here, maybe that's 1 instance, maybe it's 10, it doesn't really matter. It's pushing events onto a single segment in that stream, and we have a single reader over here happily processing the events, doing whatever logic is necessary. Maybe this is overnight when the volume is slow. What happens next is Pravega can detect the growth. People have woken up in the morning, they're starting to look at their web service or whatever, the load is starting to grow. And Pravega notices this, and he's starting to notice an imbalance between how quickly events are being pushed on and how quickly they're being read and processed. What's important is the microservice doesn't need to detect this. Pravega can do that for you. Once Pravega will do that, it will initiate a scaling event. Now at this point, what it's done, it's partitioned that into what I've put here as 2 segments. Now 2 segments here I only did simply because how much space I wanted to use there. Maybe it's 3 segments, maybe it's 5 segments. As Shrikant walked through in that heat map, it can partition it out automatically based on whichever sets of routing keys are the most heavily being hit, and lay them out so there's an even load across all of those segments. But note 2 things about this. Pravega's automatically done this. Have I changed microservice A over there in its 10 instances? Nope. It has no idea that this has happened. It was pushing events onto that stream using routing keys. It continues to do so. It's just now, instead of the routing keys all going to a single segment, Pravega's distributing them over multiple segments. No reconfiguration necessary on that producer side. How about on the consumer side? On the consumer side at this point, we can optimize the consumption of the events and gain better parallelism. But we can do it at our leisure. Pravega does not force us to do that when we originally do the scaling. At this point, we have our single reader. It's reading from 2 segments. It's inefficient, but it works absolutely fine, doesn't change any of the guarantees or any of the benefits that Pravega brings. What Pravega will do is Pravega will provide a notification. Hey, you may want to go and change your read parallelism because there's now more segments available for you to read from. If it is not convenient, you're in the middle of some complex process or something else, you can wait, no problem. But when it's convenient for you, you can do a little bit of a reconfiguration and then have those two segments, or those two microservices, and again, in a partitioned fashion, each reading off those two elements of that stream, or the two segments of the stream. Again, maybe it's 3, 4, or 5, it doesn't matter, but you can scale that out. The other thing about it is, I talked about the fact you can do this with no business impact. You can leave this person running, reading from both segments on that stream. You can establish a separate reader group with a new set of instances for these down here. Bring these up, make sure they are totally initialized, able to handle the full load, then and only then shut down the original one. So you can do a completely smooth and seamless transition, no business impact at all, completely dynamic. The only thing that has to change is the number of consumers. Everything else Pravega handles for you and is completely automatic. How about exactly once? Srikanth talked about this. This can be a major challenge, not so much if you're doing a true, just simple query, because that's generally kind of an endpoint in a microservice. But how about if there's more complex processing? This particular case, we have a whole bunch of events coming in. I renamed this to the initial microservice, but maybe it's somewhere in a pipeline. But whatever it is, there are events coming in. Some of those events wind up getting pushed out to other microservices because there's further processing that needs to happen. Some of them may not. Some of them may get processed by that initial service. There's no additional processing at that point. What happens here is there's some very subtle failure conditions based on when a service crashes and how it works with pushing the events to the later services. Let's assume, for the sake of argument, these events come in, they're nicely named A, B, C, D, E. That makes it easy in the example. You can see the order very simply. And a couple of them, A and B, maybe they generated follow-on events, A prime and B prime, which are going to the green service. And A also generated a follow-on event down to the purple service. C, for whatever reason, didn't generate any additional processing, but D did down to the purple service. And you kind of get the idea. The question comes in, what happens if you fail right at D? Now, if you look at this here, you can see, I've clearly shown D was processed, and D's side effect was generated and pushed down to that stream. But as you're restarting the microservice, how do you know that? You may know you read D, but maybe you failed immediately after you read it before the event was pushed down to the purple service. Maybe you even did all of the processing for D, were right about to make that API call to push it down, and then you failed. Or maybe you never read it at all. It's really, really tricky to distinguish those cases and be able to record that in a way that you don't accidentally either generate duplicates or, even worse, skip the processing of D. Because if you think you've processed it and pushed the event down to the purple service, but really you failed just before you made that API call, the last thing you want to do is restart and not process D, because then you've lost data down the rest of your microservices. So how can Pravega help here? This is using the Pravega transactions, and we can completely eliminate that window. So same event, same stream of events that are coming in, exact same processing. But in this case, when they're pushed out in a Pravega transaction. And the important thing about that Pravega transaction in this case, like specifically here with D, these events at this point are invisible to that service. They're there, they're durable, they're ready to go, but at this point, that process cannot see them. Why that's important is it comes back to that same failure point. We can now have much better semantics about when we record, have we processed element D or not? We can do that because of the fact that we know that that transaction doesn't get committed until we have that explicit call to do so. And we can make sure that we've recorded, I have processed element D before I commit that transaction. And only at that point, then the events are visible to the downstream services, and they can continue the processing. So the way that works is basically using a checkpoint. We can have gotten in here, we've processed element D, we can record a checkpoint, where we say, here's our stream offset. Now, obviously, we wouldn't record the offset as just past element D. It would be an offset or something like that. We can restart at that point, but that offset would be just past that element D. The other thing we record in there is we record the transaction IDs. Here are the transaction IDs that I've been building up along this way. In normal happy processing, right after I establish that checkpoint, I'm going to go and I'm going to commit those transactions. But what if that fails? I've set up my checkpoint, I'm about to commit my transaction, and the node blows up. Well, I restart the service somewhere else. It's going to go, it's going to take a look at that checkpoint, it's going to set itself up, and then it's going to go and it's going to commit those transactions. If they haven't been committed already, that's great. It just commits them and everything is wonderful. What if they have been committed? It's actually OK to commit the transaction twice. I'll come in, I say I want to commit the transaction, I get an error. That transaction has already been committed. That's OK. The system tells me the data is already done, it's already been pushed. The key is I'm not regenerating the data. I'm simply making sure I'm telling the system, make that data available to downstream applications or to downstream services. If it already is, that's no problem. I've simply told it twice to make it available, but it's still only available once. That makes, again, the job of that service much, much easier because you don't have to handle those complex cases when you have the microservices depending on each other. The transactions really provide that buffer between them and make it much easier to manage that. Last thing I want to talk about quickly. So far, the assumption has been, in everything I've talked about, that your service, your microservice, is very easy to partition amongst those different instances. And probably for 95 to 99% of the time, that is absolutely true. You can process, you can split things out by the routing key. The processing is largely independent, but that's not always true. Typically, there's a little bit of state or a little bit of management that needs to occur between the microservice instances in order to keep things straight. One of those might be like with a scaling event, when you scale up the readers. That's going to affect the microservices. They may need to collaborate about when exactly they do that, or there may be other instances. And this is where Srikanth had mentioned the use of a state synchronizer. And here I used a metronome. We've heard a lot about jazz musicians here. What does a metronome do for the jazz musicians? It keeps everybody on the same page. It's one single point that provides the timing on the music everybody can look at and see and make sure they're in time or not. In this particular case, that is a state synchronizer. What it provides basically an atomic update mechanism that all of these microservices can read it at any point, see the current state of the system. Any of them can update it at any point. But there are mechanisms in place that if two of them try to update it at the same time, one succeeds and the other fails. The other then has to go and say, OK, what's changed? He can read the latest state. If necessary, he can then reapply his change on that modified state. Or he may find the state has changed underneath him, and the change he was going to make no longer matters. The way this is implemented under the covers is Pravega has a mechanism to basically say, tell me the current ending offset of the stream. I can get that. Then I can say, I want to do a write to the stream at that offset. If that offset is still the end of the stream, my write succeeds. If somebody else got in there with a change in the meantime, my write fails, and then I have to go back and take a look at that update and see what I need to do. Very simple mechanism at its heart, but it provides a very powerful construct for keeping these services in sync and providing that atomic update. Where might you use that? Whole bunch of places. How about a global configuration? Clearly, most of the time, the microservices, when they start, they have some configuration information associated with them. They can get going. But there may be changes to that over time. You want to communicate that globally. That can be pushed in the state synchronizer. All the services will pick it up and can make the appropriate change. Similarly, task management. There may be cleanup tasks or other things that need to occur in the different services. And maybe you can't start a second round of cleanup tasks until the first one is done. Those tasks can be managed inside that state synchronizer, recorded when each individual service has done its necessary cleanup, and then you can move on to the next phase. Very much like a Hadoop model almost, where you divide the tasks out amongst, you synchronize again when they're all done, then you start the next version. coordinated via that state synchronizer. Certain elements of error handling, most error handling is going to be purely local to an instance, but maybe you want to keep some global metrics about errors or things like that that are not instance specific. State synchronizer can work there. Lots of other cases too. And again, the state synchronizer isn't designed for the 95% case. You really want that partitioning for the high-speed microservice, but it's for those fewer cases where they do need to be coordinating and collaborating. So I'm running a little bit out of time, but basically what this picture shows, you can set up a lot of these features using Pravega inside a common framework up here, where it can take over the jobs of initializing the microservice, the HA capabilities, the replaying of the stream, the checkpoint management, and so on. Inside the microservice itself, you're really down to implementing the business logic. All of the hard problems have been solved using Pravega, using transactions, using that elastic scaling, and you can focus narrowly on what are the events you need to process and what do you need to do. And that's you can focus all of your efforts on that. Basic balance between it, Pravega and framework can provide the full HA, all of the recovery capabilities, the elastic scaling, the load balancing amongst the instances, all the management of the checkpoints, the recovery from the checkpoints and everything else, all the management of the transactions. The microservice itself does the things that are really specific to it. What data model does it want? How does it want to organize the data in memory to best be able to do the business logic it needs to do? It has to implement the business logic, either their queries, their processing, whatever that business logic is, and a little bit of support for the checkpoint. That capability to take that in-memory data structure, transform it into a series of events that can be used as a checkpoint, and that ability to snarf that in afterwards and reinstantiate that. But really, that's not too much. And it really allows you to focus as a microservice developer on that core of what you need to do. So I'm going to turn it back over to Srikanth. There's more to come on Pravega, and then I think we probably have time for maybe a few questions.
Anyhow, as I mentioned, we are in the golden age of reactive programming because of 3 reasons. One is stream process, the new stream process, which make exactly once processing possible. 2 is the microservices, the emergence of microservices. And 3rd is the emergence of serverless computing. In all these 3 cases, the claim is Pravega is the ideal platform. It's not just a queuing thing. Of course, it provides PubSub under the covers, which is needed for any reactive programming. But also it provides all other features that we talked about. And Pravega is an open source and licensed under Apache 2.0. Welcome you guys to come and support. We still have to work on a few more things to kind of make it even more robust. And if you can go to our website, pravega.io, to look at the features and have more detail. And if you have any questions, please feel free to reach out to me. Without any questions, ready to take any questions.
Yes, so Pravega seems very Kafka-like to me with the partitioning and the tailing the log and all that. Other than the dynamic scaling, have you done any benchmarking against Pravega and Kafka?
Yeah, so as I mentioned, Kafka is again a messaging buffer, right? It doesn't have the elastic scaling that we talked about. It doesn't have the long-term storage that we talked about. All these things are very, very important if you want to build a real robust thing. And the way the implemented transaction is completely different because we have a separate transaction segment which we can close off when it's closed. It is not a client thing which the client has to deal with the whole data on the same thing. And second, the most important thing in messaging buffers, which is not well implemented there, is the ability to do catch-up reads and the writes not getting impacted by catch-up reads. Because that's the fundamental reason why we use messaging. The write should never be impacted by anything that's going on with your system. In our case, because the catch-up reads could be coming from different machines, the way we segment and distribute on different machines, that's never impacted, which is a very, very important feature of a messaging system. And finally, a write part is different from a read part. So the write is super efficient. We are not depending on some kind of magic buffering, but we're guaranteeing the durability which is very important to give the consistency guarantees that we're giving with the system. Right. So that's where it differs. And the distributed computing primitive that I talked about is very useful for you to write microservice applications. You don't need to have something like a zookeeper again to use for these kind of coordination between different processes.
And you mentioned that every time you do a write, you have to wait for 3 acts back.
Yes.
Is that how that seems? That's a long time. You know, that seems like it could. If those acts take a long time, that could affect your latency.
Well, but you want to give durability, you have to do that, right?
Okay, so you're sacrificing a little latency for that.
No, we don't sacrifice, because what we are doing, the trick there is that the write is super write efficient. We are not writing and reading from the same place. That's the trick that we use. But we're not guaranteeing the durability for achieving that. We achieve low latency. We do small writes very efficiently for IoT kind of use cases by making the write super efficient for that, not by sacrificing durability, by buffering them in different places and doing all that stuff.
All right, cool. No, it looks good. I'm going to have to take a look.
Thank you. Any other questions? Thank you.